Hello everybody, let's continue our journey into the wonderful world of spectroscopy. We're trying to figure out how light is going to interact with atoms. Well, eventually we'll move past atoms into more complicated things, but let's start by mostly looking at the hydrogen atom, the simplest of all the atoms. And if we can master the simplest one, then we can go from that as a stepping stone into the more difficult ones. All right, so this is going to be a pretty intense video. We are going to get into the secrets of how we are going to form those spectral lines. How is it that we form the red line that we saw in a hydrogen emission spectrum? How is it that we form it as an absorption line if we're looking at the absorption spectrum of hydrogen? How do we form just spectral lines in general? And remember, spectral lines, what I'm talking about are absorption or emission lines. They occur at the same wavelengths, and they're all related to interactions between light and atoms. Really, light and those electron energy levels I was talking about in the Bohr atom. Since this is going to be a pretty intense video, I wanted to give you a roadmap of where we're going to go, sort of an executive summary of this entire talk. What is our goal? We want to understand why absorption lines and emission lines, or so-called spectral lines, appear at very, very, very specific wavelengths. And as we learned previously, that corresponds to very specific photon energies. Why is that happening? What interaction between light as a photon and an atom is occurring to give us our absorption and emission lines? And just to sort of give you the entire roadmap, we're going to see the absorption of a photon, thus leading towards the creation of an absorption line. So an absorption of a photon will happen when an electron encounters a photon, or you can reverse that, a photon encounters an electron. And the photon has the exact energy to take that electron and move it from one of its allowed energy levels to another energy level. So it's going to move it from a lower energy to a higher energy. In essence, that electron is going to absorb the energy of a photon, and it's going to use that energy, if it's the right amount, and only if it's the right amount, to jump from one energy level to a higher energy level. This is only allowed at those very specific energy levels. So that's how we get absorption. A photon encounters an electron. That photon has the right amount of energy, the same amount of energy as wherever the electron is in an energy level to the amount of energy required to jump up to a different energy level. As long as those energies match, the photon energy and the energy to move that electron to a different energy level, then that photon will be absorbed. That electron will gain that energy that the photon had and move to a higher energy state, to a higher energy level. The electron will have been absorbed, or the photon would have been absorbed, the electron would have gained energy. Emission happens in sort of the reverse. You have an electron, it's hanging out in an excited state, it has a whole bunch of excess energy, so it's at a higher energy level, and naturally, things want to go back down to the lowest energy state. So that electron that's in a higher energy level is going to want to move down to a lower energy level. So when that happens, whenever it goes from a high energy level to a low energy level, it has to give up all that extra energy that the bigger energy level had, the higher energy level. And the way that it gives up that extra energy is it will shoot off a photon that has the exact energy for it to go from a higher energy level to a lower energy level. However much excess energy it had, it'll shoot off as a photon, and that'll allow it to jump down, to move down to a lower energy level. So that electron, by just moving closer, moving downward towards the nucleus to a lower energy level, it does that by emitting a photon to shed that excess energy. And remember, this is an executive summary. The entire video is going to give a more full explanation of all these. To get there, though, there are a couple of key things that we need to remember. Now, I've already touched on these. Electrons can only orbit the nucleus of an atom at very specific energy levels. There are no in-between levels. It can orbit at this distance with this energy, at this distance with that energy, at that distance with that energy, but nowhere in between. So there are these energy levels. There are these energies that an electron can have, and those are the only allowable energies. And those allowable energies are different for every atom, meaning that every atom on the periodic table, every element, will have its own unique set of absorption and emission lines. And photons, every photon has a very specific energy, and that energy is determined by the wavelength of light. All red photons with a wavelength of 65.63 nanometers have the exact same energy, 1.9 electron volts. So a photon that has an energy of 1.9 electron volts, you're really talking about the smallest bit of red light that has a wavelength of 656.3 nanometers. Okay, those are the key things to remember, because we're going to get those energies to match up, and that's where the interaction happens, is when things match. When they don't match, you don't get an interaction. Now, this is a pretty bland slide, but since these energy levels in the Bohr model are so weird, I decided, why don't I just show you, why don't I build a Bohr model for the simplest of the elements, hydrogen, right here. So now you can see my entire screen, my editing screen. So I have a couple of things ready to go over here. I have an electron that seems to have a letter associated with it. There we go. And what I'm going to do is I'm going to put the distances that the electron is allowed to orbit, the electron energy levels. And we're picturing them as orbits, but we know that they're really electron clouds determined by the wave function. All right, so go ahead and center that on the nucleus. And this would be, say, the first energy level, the first distance that is allowed to orbit at. So we'll just go ahead and put our electron right there. And the electron can orbit around the nucleus. And it's a certain distance away. And the positive and negative are trying to pull each other together. So it needs to maintain a certain amount of energy to keep that distance. That energy has a certain, or that electron has a certain amount of energy for this first energy level. Let's build the next energy level. I can't just build it anywhere. It's going to be a very specific distance away, going to have a very specific energy. So actually, I'm going to make this one much bigger so I can bring up 1 point. Okay, so here's our next energy level. And if I wanted to, I could say, oh, this electron has more energy. It's at a higher energy level. It can orbit at that. It can go around here. And we're going to be talking about how we can move this electron from this high energy to this low energy level, or this low energy level to this high energy level. Let's just go ahead and keep this electron in the bottom, the lowest energy state, but let's build another one. So I could build another energy level, and this one, I'm going to make it a little bit of a smaller distance because that's just how nature works. There we go. So there's our next energy level. So notice that the jump in energy from the first to the second was big, and now it's a little bit smaller, and the next one will be 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 smaller. So let's build another allowable electron energy, another allowable electron orbit, if you will. And notice that this is a big energy jump, a small energy jump, a smaller energy jump. And you can keep doing this, and you can technically do this forever. So now I've just been building my Bohr model of the hydrogen. This is the lowest energy level it can have. But if I wanted to, if I could give it some energy, extra energy, by it absorbing a photon, the photon would have the exact energy for the electron to move from here to here. Then now the electron can orbit here. I cannot have the electron orbit at that distance, at that energy. That's just not how atoms work. That's the weird part about quantum mechanics, is that that is not allowed. It can only be here, orbit at this distance, orbit at this distance, orbit at this distance, orbit at this distance, and so on and so forth. So there we go. Hopefully me actually building a Bohr model of the hydrogen atom with some of the electron energy levels helps. Now let's explore the electron energy levels and how we go about naming them and referring to them. So here I have just that same idea of that Bohr model. So here's my nucleus of a hydrogen atom. Let's start with hydrogen, the simplest of all of them. So it's just a proton. And now I'm not going to draw an electron on here, but I'm just going to draw the electron distances, the electron energy levels, the distances that the electron can orbit away from the proton. And now we have the first one, the second one, the third one, fourth one, fifth one, so on and so forth. Let's talk about how we name them. The absolute lowest energy, the energy level closest to the nucleus, this is what we call the ground state. So this first electron energy level is called the ground state. It's the first one, and we like to number things. So let's use the letter N to say this is the number one state, the first one. So it's the N equals 1 energy level. Common name of the ground state. This is where electrons prefer to be. You leave an electron alone, if it's in a higher energy level, eventually nature will make it go back down to the ground state. Everything likes to be in the lowest energy possible. So eventually the electron would like to go down to the ground state. So this is where electrons prefer to be. But you can give it a little bit of a shimmy. You can feed it a Red Bull, get it all excited, give it some extra energy. And maybe you can find it in the next energy level, a higher energy level, a farther distance away from the nucleus. And this is what we call the first excited state. We had the ground state, and then we gave it some energy. It chugged a Red Bull. It's all energized now. So it's excited, and this is the first place it can be excited. So we call it the first excited state. This is, the ground state was the number one state, the first one. This is the number two state, the N equals 2 state. And it's farther away from the nucleus, so that electron has more energy to maintain that farther away distance. It takes more energy to pull it away from the nucleus. And then we could go to the next one. If we had the ground state, then the first excited state. Let's talk about the next one. It drank another Red Bull, the second excited state. And we all know you get diminishing returns in the number of energy drinks that you drink. That first one really gets you moving. The second one, yeah, it gets you going a little bit more, but not nearly as much as the first one. So this one is not as far away, so less of a jump. It's a big jump from the ground state to the first excited state, a smaller jump from the first excited state to the second excited state. And we had the N equals 1, the N equals 2. Hey, this is the third one, N equals 3. And then we could do the third excited state, N equals 4. Then we could do the fifth excited state, N equals 5. The fourth excited state, N equals 5. The fifth excited state, N equals 6, so on and so forth. Notice that I have this ring on the outside, but eventually we can remove the electron from the atom itself. But to get to how we can actually remove the electron from the atom, we have to talk about how we actually move an electron around in an atom. So now I've put my little electron here. Here we have an electron and a proton. So we have a hydrogen atom with the electron in the ground state. Now, I do not expect you to memorize these numbers at all, but the energy difference between the ground state and the first excited state, for the electron to move up to the first excited state, it would need to gain 10.2 electron volts. That's the energy difference between those two levels. So to move up, it needs to gain, but it has to gain the exact right amount of energy because it can't exist between. So it can only gain in increments. And from the ground state to the first excited state, it needs to gain exactly 10.2 electron volts, and then it'll move up from the ground state to the first excited state. And it's all excited because it gained 10.2 electron volts of energy. We could move it up again, except to go from the first excited state to the second excited state, the energy difference there is 1.9 electron volts. So it didn't have to gain as much energy to go from the first excited state to the second excited state, from the N equals 2 to the N equals 3. And you do just have to start practicing all the naming and how we number these and how we name them. The more you write them down, the more you look at these and stare at them and play with this, the more that becomes you can just say them quickly. Okay, so to move an electron to a higher energy level, it needs to gain energy. But what goes up must come down. So whenever it's going to move from a high energy level to a low energy level, that electron is going to give up energy, it's going to release it out to the universe in the form of a photon. And it will give up exactly 1.9 electron volts. So that photon it gave off, guess what? It has exactly 1.9 electron volts of energy. And that's how we move an electron down. The electron had too much energy in the second excited state to be in the first excited state. So to jump from the second to the first, from the n equals 3 to the n equals 2, it had to shed, it had to emit, it had to give off that exact amount of energy of 1.9 electron volts. And if it wanted to go back down to the ground state, it would have to shed exactly 10.2 electron volts of energy. So give up that energy electron and move down. Pew, shoots off a photon with energy of 10.2 electron volts. So you can really see that it has to gain energy, and it'll gain electric energy to move up by absorbing photons, and then it emits them to move down to lower energy levels. Now, what happens, is there a way that we could just take this electron and remove it entirely from the atom? Something similar to, remember we talked about escape velocity? That would be the speed that if I wanted to get rid of my cell phone, because you know these things are controlling our lives. So if I wanted to say, I'm done with you and make this leave so it can never come back, then I could throw my phone, pew, and make it leave the earth forever if I threw it at the escape velocity. Does such a thing exist for an electron? Is there an energy that we can give it so it'll leave the hydrogen atom here forever and never come back? The answer is yes. If you give the electron enough energy, then it can leave forever, and it's a minimum amount of energy. For the hydrogen atom, that energy is 13.6 electron volts. So if you zap a photon in the ground state with 13.6 electron volts of energy, it'll leave the hydrogen atom forever. Well, maybe not forever. They could bump into each other later on in some sort of cosmic kismet of electrons getting back together with photons. But it'll become no longer bound to the nucleus of this hydrogen atom. And in that case, we say that the hydrogen atom has been ionized. And what we have now is an ion, a positively charged atom. It has lost one of its electrons, so it has more positive charge in the nucleus, more protons than it does number of electrons. It is a charged atom that we call an ion. And we gain a free electron that's just zooming around the universe. Okay, so we've already done pretty much the entire point of this video, but it's such a crucial and nuanced thing to understand that I want to make sure that we really get this. So when we look at absorption and emission spectra of an atom, we can understand what's going on. We're looking at the absorption. We're looking at what energies, say that hydrogen atom, has that moves an electron from one energy level to another energy level, to a higher energy level. That happens whenever the electron absorbs energy. And where is it getting that energy from? It's absorbing it from a photon that has the exact right amount of energy, which means it has a very specific wavelength, a very specific color. And it has to be the exact right amount. It's sort of jumping between these energy levels because there are no in-between energy levels. It has to be the exact right amount. 10.2 electron volts for the ground state to the first excited state for hydrogen. No other ones allowed. To go from the first excited state, the n equals 2, to the second excited state, n equals 3, it has to absorb a photon that has exactly 1.9 electron volts of energy. Otherwise, that photon will not interact with that electron, and that electron will not absorb that photon. You will not get an absorption feature at 1.9 electron volts of energy, a wavelength of 656.3 nanometers, a nice color of red. All right, so we now see that absorption is our method for an electron to gain energy by absorbing a photon that has the exact right amount of energy to make it jump between these energy levels. It's gaining energy, so it's moving farther away from the nucleus, it's moving from it's moving away from the ground state. It's moving to a higher energy level. Emission is the opposite. We have an electron in a high energy level. It has too much energy to be in a lower energy level. So when it wants to move back down to a lower energy level, it needs to emit a photon that has the exact amount of energy for it to, say, jump from the second excited state to the first excited state, or the exact amount of energy for it to jump from the first excited state down to the ground state. It releases that energy by emitting a photon that has the exact same amount of energy, so it has a very specific wavelength, a very specific color. Notice that in the absorption case, we would be gobbling up all the photons that have exact energies, creating a rainbow with little wavelengths, specific wavelengths missing in absorption spectrum. And with emission, as those electrons are moving back down and shooting off photons, pew, 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 they're shooting off photons that only have very specific wavelengths that correspond to the energy level differences in the atom that you're talking about. So if you're looking at that, and you can spread the light out, you'd only see the very specific wavelengths, the very specific energies. You'd actually be looking at the energy structure of whatever atom you're looking at, and you'd see an emission spectrum. So it has to be that exact amount of energy. And since every atom has a different number of protons in the nucleus, I mean, how do we actually number the elements in the periodic table? Hydrogen is element 1 because it has 1 proton. Helium is element 2 because it has 2 protons. Lithium is element 3 because it has 3 protons. Iron is element 26 because it has 26 protons. And that means it has a different amount of positive charges and a different amount. And so iron would have 26 protons, a positive charge of plus 26. And then you have all the electrons that balance it out. But with a different charge means that you are going to reshuffle the deck on all of those energy levels. The amount of energy to jump from the ground state to the first excited state, that differs from atom to atom. So that means that every element is going to absorb and emit certain photons. So it can move its electrons around between those energy levels, which means that every atom absorbs and emits very specific wavelengths of light, very specific energies of light, which is just another fancy way of saying that they all have their own unique absorption and emission spectra. We have just sort of uncovered something really deep and fundamental here. We can now look at the light from things coming from a celestial object. We can identify absorption and emission lines that tells us what the chemical composition is. And now we see that we're really just moving, we are detecting how the electrons are moving around in those atoms, because that's what's creating these absorption and emission lines. When we look at an absorption or emission spectrum, we're actually looking at the energy structure of an atom. That is crazy. That's like a weird, makes it feel like you have this intimate interaction when you look at a spectrum of an element, because you're actually seeing its energy levels. Okay, so let's go ahead and, if you need to pause, because this is a pretty big video, take a pause, step back for a second. But I want to talk to you about actually how we're forming those spectral lines. So this part is going to be largely review, but it's also going to be demonstrative of how this actually occurs in our hydrogen atom. So if you took a break, welcome back. Let's go ahead and jump right in, because I want to talk to you about how we're going to form those spectral lines, how we're going to form absorption and emission lines. And we're going to do it playing with the simplest of all atoms, the hydrogen atom. So here I have my Bohr model of hydrogen. Here is my proton. Here are my allowable electron orbits, my energy levels. And notice that I've labeled the energy difference for 2 of them. The amount of energy that the electron needs to go from the ground state to the first excited state for hydrogen is different for every other element. For hydrogen is 10.2 electron volts. For it to go from the first excited state to the second excited state, the n equals 2, the n equals 3, there's an energy difference between those levels of 1.9 electron volts. So here I have just a graphic. What we're going to do is we're going to take a photon, a UV photon that has an energy equal to the right amount of energy the exact amount of energy for the gap between the ground state and the first excited state, the amount of energy this electron needs to go from the ground state to the first excited state, to go from the n equals 1 to the n equals 2 state. What we're going to do is we're going to take one of these photons, has a wavelength of 121.6 nanometers. You can go ahead and figure that out. The energy maps to the wavelength maps to the energy. And what we're going to do is I'm going to fire this photon that has a tasty energy to the hydrogen atom, 10.2 electron volts. So if it's flying through a cloud of hydrogen atoms, it's going to find a hydrogen atom that has this electron in the ground state. And what happens? So here comes the photon, finds an electron in the ground state. That electron absorbs it and it jumps to a higher energy level. So now we have this excited electron. Although it doesn't like to stay in an excited state, everything likes to go to its lowest energy state. Remember, nature is always pretty lazy. So what it's going to do is it's going to shed that excess energy and it's going to fall back down to the ground state. This happens in about 10 to the minus 8 seconds on average. So it really, really wants to leave the first excited state and get back down to the ground state. How is it going to do it though? It has too much energy. 10.2 electron volts, too much energy for it to live in the ground state. So what it's going to do is it's going to shed 10.2 electron volts of energy, that exact same ultraviolet photon, but whenever it sheds it, it's just going to happen in any random direction. So it's light can be coming in, say we have a star down here. Oops, we have a star down here off of screen. And it's sending in UV photons of 10.2 electron volts into a cloud of hydrogen. Those wavelengths are going to get gobbled up by hydrogen atoms to excite from the first excited state, or from the ground state to the first excited state. And then those electrons are going to shed that energy by firing off a photon that has the exact same amount of energy to go back down to the ground state. So this case where we have an electron that absorbs a photon, so it jumps to a higher energy level, and then it immediately jumps back down to the same energy level. So it absorbs a photon with 10.2 electron volts, for example, and then re-emits a photon with an energy of 10.2 electron volts. It absorbs a photon with 121.6 nanometers wavelength, and then it re-emits that same photon with 121.6 nanometers, but now in a new direction. We call that scattering. Light comes in from one direction, interacts with our hydrogen atom here, and then leaves in a random direction. So it comes in this way, and then it goes that way, comes in this way, goes out that way, comes in this way, goes over that way, comes in this way, goes that way. And we call this scattering. Kind of like if you have a bunch of pool balls on a table and you ram the cue ball into it, all the pool balls scatter. They shoot off in different directions. And notice now we had one photon in, one photon out. So that's one way. And we could do the same thing where if we send in a red photon, 1.9 electron volts, it would find a hydrogen atom that has this electron in the first excited state. That electron would go, I like me some 1.9 electron volt energy photons. I like my red photons. Gobble them up and use that to jump from the first excited state to the second excited state. And then it could go from the second excited state back down to the first excited state in a scattering. Okay, so that's one method. All right, now we're going to get a little bit more complicated. So don't worry about the text yet. The animation I'm about to show you is supposed to walk us through the text. So now what I'm going to do is I'm going to send in a ultraviolet photon that has a higher energy than the previous example. It has 12.1 electron volts of energy. Let me do some quick math. 10.2 plus 1.9 is 12.1 electron volts of energy. So this ultraviolet photon with 12.1 electron volts of energy would have a wavelength of about 102.5 nanometers. That is the right amount of energy for an electron in the ground state of hydrogen to jump all the way from the ground state, skip the first excited state, and go straight into the second excited state, to jump from 1 to 3. So let's send in that photon, and the electron is going to, boom, jump directly to the second excited state. Now, our electron has options. it could go from the second excited state and jump right back down to the ground state, a scattering, and fire off a photon with 12.1 electron volts of energy, the energy difference between the n equals 3 and the n equals 1, the second excited state and the ground state, just like we saw in the previous slide. Or maybe this electron wants to take a meandering path home. It wants to cascade back down. It wants to check out. It's heard great things about the first excited state. So our electron, it could go from the second excited state down to the first excited state. But to do that, it would have to shed that 1.9 electron volts, that excess energy. How does it do that? It sheds it by firing off a red photon with 1.9 electron volts of energy. That's a wavelength of 656.3 nanometers for the hydrogen atom. Okay, so now it's in the first excited state. I just said that it doesn't like to be in the first excited state. It wants to go back home. It wants to go to the ground state. So how can it go to the ground state? Well, it can fire off a photon that has 10.2 electron volts, the energy difference between those two energy levels, and go back down to the ground state. So in this case, it absorbed one photon and then cascaded back down to emit two photons with different wavelengths. So we sent in an ultraviolet photon of one energy, we got out an ultraviolet photon of a different energy, and then a red photon. When we have something like this, we send in a high energy photon, it excites an electron, and then that electron cascades through energy levels back down to the ground state, emitting a bunch of photons. That is called fluorescence. That's how fluorescent light bulbs work. And notice that the two photons that it's giving off, one photon in, two photons out, one photon in, and the two photons out, 1.9 electron volts plus 10.1 electron volts, equals the same energy that it originally absorbed. So the energies are always balanced. All right, so I know that was pretty complicated, but now we understand absorption and emission. Here we're going to have, here we have the absorption of a photon, 12.1, a very specific color of light, 102.5 nanometers, ultraviolet. And we've seen how an atom can emit a photon, how we can form emission lines, and why there are very specific wavelengths, very specific energies, because you're just watching the electron, say, go from the second excited state to the first excited state. And to do that, it has to give up a red photon. It emits a red photon with an energy of 1.9 electron volts. And then it can go back to the ground state, but it has to give up that 10.2 electron volts of energy, so it emits a photon. So if you're staring at a collection of hydrogen atoms that were excited, and you're watching the electrons fall back down to the ground state, you would see an emission spectrum of hydrogen. That's why hot hydrogen gas gives off an emission spectrum of hydrogen with these very, very specific wavelengths. You're literally seeing the energy structure of the hydrogen atom when you look at an emission spectrum of hydrogen. Same one as when you look at an absorption spectrum. Thank you for bearing with me for this pretty complicated topic. It is sort of the combination of what's going on in this tiny scale so we can understand the universe in the largest scales. A key part to astronomy, this is the heart of spectroscopy. I hope that you rewatch this video and you truly appreciate how powerful and how amazing what we just experienced is. All right, I will see you in the next video.